Right now, in the cold and the silence a million miles beyond the Earth, a mirror made of gold gathers light that left its source before the Earth existed, before the Sun existed, before almost anything you have ever known existed. That light has been traveling for more than 13 billion years, crossing a distance so vast that to describe it in ordinary words is to drain it of meaning. When that light began its journey, the universe was a different place. There were no planets, there were no rocky worlds, no oceans, no continents drifting on molten stone. There was only a young and glowing cosmos, barely emerged from its own beginning, and a single faint smudge of something that should not have been there at all. That smudge is a galaxy. We have given it a name made of letters and numbers, the cold designation of a catalogue entry. But what matters is not its name. What matters is its age. The light we are catching tonight left that galaxy when the universe was only about 290 million years old. That is less than 2% of the age of everything. If the entire history of the cosmos were compressed into a single calendar year, this galaxy was already shining before the end of the first week of January. And it was not a faint, struggling spark. It was bright. It was massive. It was, by every expectation we carried into the age of the great telescopes, far too developed, far too soon. Yet there it is. The light does not lie. The galaxy is real, and it is old beyond what our models said was possible, and its existence presses against the most carefully constructed timeline in all of science. The story of how the universe grew from a formless beginning into the structured cosmos we see tonight. Here is what will shatter everything you think you know about the beginning of time. The story we tell about the first billion years may be incomplete in a way we are only now beginning to understand, and the evidence is arriving not as a theory or a guess, but as light, ancient and undeniable, falling onto a mirror in the dark. If you enjoy slow, calming journeys through the deep mysteries of the cosmos, journeys built to let your mind wander and your body rest, do me a small favor and hit that like button and subscribe. It genuinely helps this channel grow and lets me keep making these deep dives for you. So make yourself warm and comfortable. Let the lights go low. We are about to travel back to the very edge of time, to the first faint glow of the first galaxies, and to a discovery that has quietly unsettled the people who study the beginning of everything. Let's begin. To understand why a single galaxy could trouble the minds of cosmologists, you first have to understand the number that frames everything. The universe, we believe, is 13.8 billion years old. That number sits at the foundation of modern cosmology, as solid and load-bearing as any number in science. But it did not arrive all at once. It was assembled, slowly, over more than a century, by people who often did not realize what they were building. The history of that number is the history of how humanity learned that the universe had a beginning at all, and it is worth walking through it slowly, because every step makes the previous step feel smaller, until at last you arrive at a truth so large it is difficult to hold in the mind. For almost the entirety of human existence, people assumed the universe was eternal and unchanging. The stars were fixed. The heavens were permanent. A person born 20,000 years ago, looking up from a fire on a cold plain, saw the same constellations we see, and assumed, reasonably, that they had always been there and always would be. This was not foolishness. It was the only conclusion the evidence supported. The night sky changes so slowly that across 1,000 human lifetimes it appears frozen. Eternity was not a belief. It was an observation. The first crack in that eternity came not from a grand theory, but from a careful measurement, made by a quiet astronomer staring at the faint light of distant spiral nebulae. In 1912, an American astronomer named Vesto Slipher, working at the Lowell Observatory in Flagstaff, Arizona, began studying the light from these mysterious smudges in the sky. Nobody yet knew what they were. Some thought they were clouds of gas inside our own galaxy. Slipher used a technique called spectroscopy, spreading the light into its component colors the way a prism spreads sunlight into a rainbow, and he noticed something strange. The light from most of these nebulae was shifted toward the red end of the spectrum. This shifting of light carried a hidden message. When an object moves away from you, the waves of light it emits get stretched, and stretched light appears redder. It is the same reason the pitch of a siren drops as an ambulance passes and races away. Slipher had discovered that almost all of these nebulae were moving away from us, and not slowly. They were receding at hundreds of kilometers every second. He did not know what it meant. He simply recorded it, faithfully, measurement after measurement, in the cold hours of the Arizona nights. This is the patient and unglamorous reality of discovery. The man who first measured the expansion of the universe did not know that was what he had done. The meaning of those measurements would be assembled by others. In 1927, a Belgian priest and physicist named Georges Lemaitre, working through the equations of Albert Einstein's theory of gravity, proposed something audacious. He suggested that the universe was not static at all, but expanding, and that if you ran that expansion backward in time, everything would draw closer and closer together until it converged on a single, unimaginably dense point. He called it the primeval atom. The universe, he proposed, had hatched from a single seed. It was perhaps the most radical idea in the history of science, and it came from a man who saw no conflict between the equations of physics and the contemplation of beginnings. Einstein himself, when he first heard the idea, was unimpressed. He is reported to have told Lemaitre that his mathematics was correct, but his physics was abominable. The notion of a beginning offended the deep human preference for an eternal, stable cosmos. But mathematics does not bend to preference, and neither, ultimately, does evidence. Within just a few years, the evidence began to arrive, and it arrived from a mountaintop in California, from a man peering through what was then the largest telescope on Earth. In 1929, the American astronomer Edwin Hubble, working at the Mount Wilson Observatory above Los Angeles, published a result that would rearrange the cosmos. He had measured the distances to a number of galaxies, using a brilliant method built on the work of an earlier and too often forgotten astronomer named Henrietta Swan Leavitt, who had discovered a way to measure cosmic distances using a special class of pulsing stars. Hubble combined those distances with the redshifts Slipher had measured, and he found a relationship that was almost too clean to believe. The farther away a galaxy was, the faster it was rushing away from us. Consider what this means. It means the universe is expanding, every part of it stretching away from every other part, like raisins in a rising loaf of bread, each one drifting from all the others as the dough swells. And if everything is flying apart now, then in the past it was closer together. Run the film backward far enough, and you reach a moment when all of it, every galaxy, every star, every atom that would ever exist, was crowded into a state of incomprehensible density and heat. The universe had a beginning, not a metaphorical beginning, a real one, a moment before which the concepts of space and time as we understand them may not even apply. The name we use for that beginning was born as an insult. In 1949, the British astronomer Fred Hoyle, who personally disliked the idea of a sudden origin and preferred a universe in continuous eternal creation, was speaking on a radio broadcast for the British Broadcasting Corporation. Searching for a way to describe the rival theory dismissively, he called it the idea of a Big Bang. The phrase was meant to sound crude, almost ridiculous. Instead, it stuck, and it became the name of the most successful scientific model of cosmic history ever devised. There is a quiet lesson in that. The labels we attach to the universe rarely capture its dignity. The universe does not care what we call it. But a name and an expanding universe were not yet a confirmed beginning. A theory is only as strong as the predictions it makes, and in the 1940s, a small group of physicists made a prediction so bold and so specific that, if confirmed, it would settle the question almost beyond doubt. A Russian-born physicist named George Gamow, along with his students Ralph Alpher and Robert Herman, reasoned through what a hot, dense early universe would have been like. They argued that if the cosmos truly began in a state of extreme heat, then that heat should not have simply vanished. It should still be here, all around us, faded and stretched and cooled by billions of years of expansion, but present, a faint afterglow filling all of space. They calculated that this afterglow would now appear as a whisper of microwave radiation, corresponding to a temperature only a few degrees above absolute zero. It was a remarkable prediction, the kind that seems almost like a dare thrown across the decades. And then, for a long while, almost nobody followed up on it. The prediction sat quietly in the scientific literature, waiting, the way ancient light waits in the dark. The confirmation, when it finally came, would arrive by accident from two engineers who were not looking for the beginning of the universe at all, but were instead trying to get rid of an annoying hiss in a piece of equipment. In 1964, two radio astronomers named Arno Penzias and Robert Wilson, working at the Bell Telephone Laboratories in Holmdel, New Jersey, were trying to use a large, horn-shaped antenna to study faint radio signals from space. They kept encountering a persistent background noise, a steady hiss that came from every direction in the sky, no matter where they pointed the instrument or what time of day they listened. They checked everything. They cooled their detectors. They suspected interference from the city, from the equipment, from anything they could think of. At one point they discovered that pigeons had been roosting inside the antenna, leaving behind what they politely called a white dielectric material, and so they climbed inside and cleaned it out and shooed the pigeons away. Still the hiss remained. The hiss remained because it was not a malfunction. It was the universe. Penzias and Wilson had stumbled, without intending to, onto the faint afterglow that Gamow and his students had predicted nearly 2 decades earlier. They were hearing the cooled remnant of the heat of the early cosmos, the radiation released when the universe was young and hot and dense, stretched across billions of years into a faint microwave glow. When they learned that a group of physicists just a short distance away at Princeton University had been preparing to search for exactly this signal, the pieces fell into place. The accidental hiss was the echo of the beginning. It was the smoking evidence that the universe had once been hot, dense and small, and that it had been expanding and cooling ever since. This is the way the great truths often arrive, not with trumpets but with an irritating noise that two careful people refuse to ignore. The discovery would earn Penzias and Wilson the highest honor in physics, and it would transform the Big Bang from a contested idea into the foundation of modern cosmology. From the temperature of that afterglow, from the precise way galaxies rush apart, and from the measured abundance of the lightest chemical elements forged in the first minutes of cosmic history, scientists slowly converged on the number that anchors everything. The universe is 13.8 billion years old. Not eternal, not unchanging, finite, and with a beginning we can almost touch. To feel the weight of that number, you have to try to scale it against a human life, and then watch the comparison collapse. A long human life lasts perhaps 80 or 90 years. If you laid out the entire age of the universe as a single mile-long road, and you placed every human life that has ever been lived end to end along that road, all of recorded history, every empire, every war, every birth and death since the first written word, would occupy a stretch shorter than the width of a single human hair at the very end of that mile. We are a flicker at the close of an enormous story, and we have only just learned to read the opening pages. And yet here is the crushing truth that sets this entire journey in motion. Within that vast span of 13.8 billion years, there is a sequence, a timeline, a carefully reconstructed order in which things were supposed to happen. The first stars were supposed to form at a certain time. The first galaxies were supposed to assemble at a certain pace. Structure was supposed to grow slowly, gradually, gathering itself across hundreds of millions of years, like sediment building into stone. The early universe was supposed to be simple, dim, and sparse. But the light now falling onto a golden mirror a million miles from Earth is telling us that something in that orderly story is wrong. The first chapters of the universe were not as empty as we believed. Something was already there, fully formed, glowing in the dark, far too early to make sense. To understand how a galaxy could be too early, you first have to understand the strangest and most beautiful property of light. Light is slow. We do not usually think of it that way, because in our daily lives it seems instantaneous. Flip a switch and the room is lit. Glance across a field and you seem to see it at once. But light has a speed, a finite and absolute speed, and across the distances of the cosmos that speed becomes agonizingly, gloriously slow. Light travels at a little over 186,000 miles every second. That is fast enough to circle the Earth more than 7 times in the span of a single heartbeat. And yet, against the scale of the universe, it crawls. This finite speed has a consequence so profound that it took humanity centuries to fully absorb it. Because light takes time to travel, every time you look at something far away, you are not seeing it as it is, you are seeing it as it was. When you look at the sun, you see light that left it about 8 minutes ago. The sun you see is the sun of 8 minutes in the past. If the sun were to vanish in this instant, you would feel nothing, see nothing, suspect nothing, for 8 more minutes, until the last of its old light arrived and the sky went dark. To look at the sky is to look into the past. There is no other way to see. This distinction matters enormously because it transforms a telescope into something far stranger than a magnifying glass. A telescope is a time machine. It does not show us the distant universe as it is tonight. It shows us the distant universe as it was when its light departed. The farther away an object is, the longer its light has travelled, and the further back in time we see it. Look at a star 1,000 light years away, and you see it as it was 1,000 years ago, when the people of medieval Europe were building cathedrals. Look at a galaxy 1 billion light years away, and you see it as it was 1 billion years ago, when the most complex life on Earth was barely more than soft-bodied creatures in ancient seas. Now extend that perspective across the entire reach of the cosmos. If you could build a telescope powerful enough to see an object more than 13 billion light years away, you would be seeing it as it was more than 13 billion years ago. You would be looking back almost to the beginning of time itself. And this is precisely what the great space telescopes are built to do. They are not merely instruments of magnification. They are instruments of memory. They allow us to read the universe the way a geologist reads layers of rock, with the deepest layers being the oldest, except that here the layers are not stone but distance, and reading them means peering across the abyss of cosmic time. But there is a complication, and it is the same complication that Vesto Slipher noticed more than a century ago. The universe is expanding. As light travels across billions of years, the very space it moves through is stretching, and the light stretches with it. Its waves grow longer, its colour shifts toward the red, and then beyond red entirely, into the infrared, into wavelengths the human eye cannot perceive at all. The light of the most distant galaxies has been stretched so severely by the expansion of the universe that it no longer arrives as visible light. It arrives as infrared, as a kind of heat glow, invisible to us and to ordinary telescopes alike. This stretching of light is measured by a single number that astronomers call redshift, and it is the most important number in this entire story. A small redshift means a small stretch, a nearby object, a recent past. A large redshift means an enormous stretch, an object near the edge of the observable universe, a past so deep it approaches the beginning. The galaxy whose light is falling onto a golden mirror tonight has a redshift of about 14.3. That number may sound modest. It is not. A redshift that high means its light has been stretched to more than 15 times its original wavelength. It means we are seeing across nearly the entire history of the cosmos, to a galaxy that existed when the universe was a small fraction of its present age. To capture light stretched that far into the infrared, you need a telescope built specifically to see heat, and you need to keep that telescope colder than almost anything else in the solar system. This is why the James Webb Space Telescope, which launched on the 25th of December in the year 2021 from a spaceport in Kourou, French Guiana, was not placed in orbit close to the Earth. It was sent to a special point in space about 1 million miles away, on the far side of the Earth from the Sun, where it could unfold an enormous sunshield the size of a tennis court and hide in its own perpetual shadow. The instrument operates at a temperature only a few tens of degrees above absolute zero. It must be that cold, because warmth is light, and any heat from the telescope itself would drown out the faint infrared whispers of the early universe. To see the first galaxies, you must build an eye colder than almost anything around it, and then you must be patient. Consider what this telescope was designed to find. The standard story of cosmic history, the timeline assembled from a century of patient observation, describes a very specific sequence of events in the early universe. For roughly the first few 100,000 years after the beginning, the cosmos was so hot and dense that it was opaque. Light could not travel freely. It bounced endlessly among a fog of charged particles, the way light cannot pass cleanly through the interior of a star. The universe was a glowing, impenetrable haze, like the inside of a cloud lit from within. Then, about 380,000 years after the beginning, the universe had expanded and cooled enough for something decisive to happen. The charged particles, electrons and protons, finally combined to form neutral atoms of hydrogen and helium. Scientists call this moment recombination, and it changed everything. Once the particles became neutral atoms, light could suddenly travel freely. The fog lifted. The universe became transparent for the first time, and the light that was set free in that moment, that first clear flash across a newly transparent cosmos, is the very same light that Penzias and Wilson would accidentally detect billions of years later as a faint microwave hiss. The afterglow we call the cosmic microwave background is, quite literally, the oldest light it is possible to see. It is a photograph of the universe at the age of 380,000 years, the surface beyond which no telescope can ever peer, because before it the universe was simply not transparent. If you could have been present at that moment of recombination, the entire sky in every direction would have glowed a deep, dull red, like the inside of a vast furnace cooling toward darkness. And then, slowly, that glow faded. As the universe kept expanding, the released light stretched and dimmed, and the cosmos entered a long, strange, lonely epoch that astronomers call, with unusual poetry for a scientific field, the cosmic dark ages. There were no stars yet. There were no galaxies. There was only a vast and silent expanse of cooling hydrogen and helium gas, drifting in the dark, lit by nothing, settling under the patient pull of gravity into slowly thickening clouds. For tens of millions, perhaps a few 100 million years, the universe was without light. It was an immense and featureless night. This is the part of the story that matters most for our journey, so let us move through it slowly. According to the standard timeline, structure in the universe was supposed to build itself gradually, from the bottom up. Tiny variations in the density of the early cosmos, faint ripples imprinted in those first moments, acted as seeds. The slightly denser regions pulled in more gas through gravity, growing denser still, in a process that fed on itself over enormous stretches of time. The first objects to form were not grand galaxies. They were modest clumps. The first stars, when they finally ignited in the darkness, were thought to be enormous, simple and short-lived, built only from the primordial hydrogen and helium, with none of the heavier elements that would later enrich the cosmos. These first stars are called population 3 stars, and no one has ever directly seen one. They are a theoretical necessity, the predicted first sparks in a dark universe, blazing brilliantly and dying quickly, seeding the first heavy elements when they exploded. From these first stars and their debris, the first small galaxies were supposed to assemble, gradually, merger by merger, like streams joining into rivers and rivers joining into a great flow. Small things first, larger things only later. This bottom-up, slow and steady picture of cosmic assembly is called hierarchical structure formation, and it has been one of the bedrock predictions of modern cosmology for decades. It is woven into the equations, It is built into the computer simulations. It is, in a very real sense, the expected shape of the early universe. And the shape it predicts is sparse. In the standard picture, the universe 200 to 300 million years after the beginning should have been a place of only the faintest, smallest, dimmest first structures. A few primitive clumps of stars, a scattering of modest, immature proto-galaxies, still gathering themselves, still thin and disorganized, not yet grown into anything we would recognize as a proper galaxy. To form a large, massive, brightly shining galaxy takes time. It takes the slow gravitational gathering of enormous quantities of gas. It takes generation after generation of stars being born, living and dying. It takes, by every model we had constructed, far more time than the early universe had available. This is the central tension, and it is worth stating as plainly as possible. The timeline says the early universe was a slow, dim, gradual place, where galaxies were small and growing and rare. The standard model does not merely suggest this, it requires it. The entire architecture of cosmic history depends on structure forming at a particular measured pace, governed by the pull of gravity, the amount of matter available, and the rate at which the universe expands. Speed up that process too much, and the careful agreement between theory and observation, an agreement that has held for decades and spans everything from the microwave background to the distribution of galaxies across the sky, begins to fray. So this was the expectation that astronomers carried, as they prepared to point the most powerful telescope ever built toward the deepest reaches of the early universe. They expected to find the faint beginnings of things. They expected smudges, fragments, the dim first whispers of structure, hard to detect, barely there, exactly as the timeline demanded. They expected, in short, to see the early universe being shy and slow and young. What they found instead would force some of the most respected minds in the field to ask a question they had not seriously expected to ask in their lifetimes. They would find themselves wondering whether the timeline, the great and trusted timeline assembled over a century of careful work, might be telling us only part of the truth. The story of how we came to look so deeply into the past begins with one of the most nerve-wracking engineering feats ever attempted. The James Webb Space Telescope had been imagined, designed, delayed, redesigned, and delayed again across more than 2 decades. It cost roughly $10 billion. It carried a primary mirror more than 21 feet across, far too large to fit inside any rocket in its finished shape, and so it had to be folded, like an enormous piece of golden origami, and then unfolded once it reached space. Hundreds of individual steps had to execute flawlessly, in sequence, in the cold and the dark, with no possibility of repair. If any single critical step failed, the entire mission, 2 decades of work and $10 billion, and the hopes of a generation of astronomers, would be lost. On the 25th of December in the year 2021, the telescope rose from its launch pad in French Guiana on a column of fire and climbed away from the Earth. Then began the long and silent unfolding. Over the following weeks, the sunshield extended layer by layer, each layer as thin as a human hair, until it spread to the size of a tennis court. The mirror segments swung into position, the whole structure cooled slowly toward the deep chill it needed to function. Engineers on the ground watched each step through streams of data, holding their breath, knowing there was nothing more they could do but wait and hope. And one by one, every step succeeded. The telescope reached its distant outpost 1 million miles away, unfolded itself perfectly, and opened its golden eye on the universe. This is the calm reality of how humanity now sees the beginning of time. Not through a sudden flash of insight, but through patience, engineering, and a willingness to gamble enormous resources on a single unrepeatable act of unfolding in the dark. When the first images arrived, they were so sharp and so deep that they stunned even the scientists who had spent their careers preparing for them. A patch of sky no larger than a grain of sand held at arm's length. A patch that to the naked eye contains nothing at all. blossomed under the telescope's gaze into thousands of galaxies, each one a city of stars, many of them so distant that their light had travelled for the better part of the age of the universe. To appreciate how staggering this truly is, consider what one of those tiny, deep patches of sky actually contains. In a single image, in a region of the heavens that you could blot out with the head of a pin held at arm's length, there are more galaxies than there are people in a large city. Each of those galaxies holds tens of billions, sometimes hundreds of billions, of stars, and many of these galaxies are being seen as they were when the universe was young. The deeper the telescope looks, the further back in time it sees, and the early universe, which the old timeline insisted should be nearly empty, kept filling the images with light. The first surprises came quickly, and they came from a galaxy that had already been a record holder. Years before the new telescope launched, the older Hubble Space Telescope had spotted a remarkably distant galaxy, identified in the year 2016 by a team led by the astronomer Pascal Oche. This galaxy, with a name made of letters and numbers, appeared to lie at a redshift of about 11, meaning its light had left it when the universe was only about 400 million years old. At the time, it was the most distant galaxy ever confirmed, and it sat right at the edge of what the old telescope could detect. It was a faint and lonely outlier, a single data point pushing against the limits of the possible. When the new telescope turned its gaze toward that same galaxy, it confirmed the distance with far greater precision and revealed the object in startling detail. But this was only the beginning. The new telescope was not built to find one distant galaxy at the edge of detection. It was built to find them by the dozens, and then by the hundreds, and to push the frontier of the observable past back further than anyone had managed before. Within months of beginning its work, the telescope began returning candidate galaxies at redshifts that would have seemed almost fantastical only a few years earlier. Galaxies at redshift 12, at redshift 13, and then, in observations that took the breath away, candidates at redshift 14 and beyond. Here is the problem that began to take shape. It was not simply that these galaxies were distant, though they were the most distant objects humanity had ever seen. It was that there were so many of them, and that so many of them were so bright. A faint, struggling smudge at the edge of detection is one thing. The standard timeline could accommodate a few rare, dim, primitive proto-galaxies in the early universe, but the telescope was finding early galaxies that were not faint and not struggling. They were luminous. They shone with the light of enormous numbers of stars, and luminosity in the early universe is a deeply troubling thing, because brightness means stars, and stars in those quantities mean mass, and mass in those quantities means time. Time to gather the gas, time to form the stars, time that the early universe, by the old reckoning, simply did not have. To make sense of this, you have to understand a crucial and somewhat counterintuitive point about how astronomers read these distant objects. When the telescope detects a galaxy at redshift 14, it is not seeing a sharp, detailed picture of swirling spiral arms. It is detecting a faint point or smudge of infrared light, and from the precise way that light is stretched and coloured, it can deduce the redshift, and therefore the distance, and therefore the time. From the total brightness, combined with the known distance, it can estimate how much light the galaxy is actually producing, and from the amount of light, it can estimate how many stars must be present, and how much total mass those stars represent. Each step in this chain is built on careful physics, refined over decades, but the conclusion that emerges from the chain is what unsettles people. The conclusion is that some of these galaxies, glimpsed only 200 or 300 million years after the beginning of the universe, appear to contain enormous masses of stars, not a handful of primitive first stars, not a small, struggling clump. In some cases, the inferred mass approaches the scale of substantial galaxies, the kind that the standard timeline says should take far longer to assemble. It is as though you were watching a time-lapse film of a forest growing from bare ground, expecting to see, after a few minutes, only the first faint sprouts breaking the soil, and instead you saw towering, mature trees, fully grown, casting long shadows, where there should have been nothing but seedlings. Consider what this means for a person trying to hold the timeline together. The universe in this era was less than 300 million years old. The light from these galaxies tells us they were already forming stars, already bright, already massive, already organized. To build a galaxy of significant mass, you must first wait through the dark ages for gas to gather. Then you must form the first stars. Then those stars must live and die and enrich the surrounding gas. Then new generations of stars must form from the enriched material. Each of these phases takes time measured in tens or hundreds of millions of years. And yet here were galaxies that appeared to have completed a great deal of that work when the universe had barely begun. This is the unsettling reality of what the telescope found. It did not find an empty early universe with a few faint first lights, as the timeline predicted. It found an early universe that was, in places, surprisingly full, surprisingly bright, and surprisingly grown up. The cosmic dawn, it seemed, had arrived earlier and burned brighter than anyone had dared to expect. And the more the telescope looked, the more of these early luminous galaxies it found. They were not rare flukes at the edge of detection. They appeared again and again, in survey after survey, a recurring pattern that could not be easily dismissed as a single strange mistake. The astronomers running these deep surveys gave them names that have become familiar in the field. One great campaign, designed to stare into a patch of sky for an enormous total time and tease out the very faintest and most distant objects, was called the JWST survey, a name built from the words for the deep extragalactic survey the telescope was conducting. Another major program, scanning a wider region to catch rarer, brighter early galaxies, was known by the name SEERS. These were not casual snapshots. They were among the deepest and most carefully designed observations ever made of the early universe, conducted by large international teams, scrutinized and reanalyzed and checked and rechecked, precisely because their results were so surprising. And the surveys kept pushing the frontier back. In the year 2024, astronomers confirmed a galaxy at a redshift of about 14.3, the most distant galaxy ever spectroscopically confirmed at that time, its light having left it when the universe was only about 290 million years old. This is the galaxy whose light frames our journey tonight. And it was not merely distant, it was unexpectedly luminous and surprisingly large for its era, bright enough and substantial enough that its very existence, at that early moment, posed sharp questions for the models. A galaxy that should have been a faint and primitive whisper was instead a clear and substantial voice, calling across nearly the entire history of the cosmos. The mathematics become even more striking when you stack these discoveries against one another. One galaxy at an impossible-seeming early time might be a measurement error, a trick of the light, a misread of the data. Two might be coincidence, but a steady accumulation of bright, massive early galaxies found by different teams, in different patches of sky, using different analysis methods, begins to look like something else entirely. It begins to look like a pattern. And patterns in science are not easily ignored. A single anomalous result can be explained away. A pattern demands an explanation, and the explanation, in this case, seemed to point toward a flaw somewhere in the great timeline of cosmic history. It is worth pausing here to be honest and careful, because this is science, not melodrama, and the people doing this work are cautious by training and by temperament. The first response of a good scientist to a surprising result is not excitement, but suspicion, directed first and foremost at the result itself. Before anyone concludes that the timeline of the universe is wrong, they must rule out the far more mundane possibility that the measurements are wrong, or that the methods used to infer mass and distance contain hidden errors, or that the early universe is doing something perfectly consistent with known physics that we simply had not anticipated. The tension is real, but the resolution, if there is one, might lie in any number of places, and not all of those places require rewriting the foundations of cosmology. Still, the unease was undeniable, and it was felt most acutely by the very people most invested in the Standard Model. When the first reports of these surprisingly massive early galaxies appeared, they did not arrive quietly. They arrived as a genuine jolt to the field, the kind of result that makes a cosmologist set down their coffee and stare at the data again, and then again, looking for the mistake that surely must be there. Some of the most striking claims came from a study that would soon be described, half in awe and half in alarm, as the discovery of galaxies that might break the universe. And to understand why those words were used, and whether they were justified, we have to look closely at exactly what that study found, and at the storm of scrutiny that followed it. The study that crystallized the unease arrived in early 2023, published in one of the most respected scientific journals in the world, led by the astronomer Ivo Labbé and his collaborators, including the astronomer Peter van Dokkum, and a team of researchers scattered across several institutions. They had been examining some of the earliest deep images returned by the new telescope, and they had identified a small set of galaxies that appeared to be both extremely distant and extremely massive. The light from these galaxies suggested they existed when the universe was only about 500 to 700 million years old, and the masses they inferred were not modest. Some of these galaxies appeared to contain as many stars as the entire Milky Way galaxy contains today. Sit with that comparison for a moment, because it is the heart of the matter. The Milky Way is a mature, grand spiral galaxy, the product of more than 13 billion years of growth, of countless mergers, of generation upon generation of star formation, stretching across nearly the entire age of the universe. It holds something like 100 billion stars, and here were galaxies that appeared to have assembled a comparable quantity of stars when the universe was barely 500 million years old, less than 4% of its current age. It was as if a child, only days old, had somehow grown to the full height and strength of an adult, complete and developed, where there should have been only the first fragile beginnings of growth. This is the disturbing reality that the study laid out. To form that many stars that quickly, the early universe would have had to convert gas into stars at a rate far higher, far more efficient than the standard models allowed. There is, in cosmology, a kind of cosmic speed limit on how fast a galaxy can grow, set by the amount of ordinary matter available in the early universe, and by the time it takes for gravity to gather that matter and forge it into stars. The galaxies in this study seem to brush against that limit, or in the most extreme interpretations to exceed it. And when an observation seems to exceed a fundamental limit, it sends a tremor through the foundations. The reaction in the scientific community was immediate and intense. Some researchers spoke, only half in jest, of galaxies that should not exist, of objects that broke the universe, of a crisis at the dawn of time. Headlines around the world declared that the Great Telescope had overturned the Big Bang, that cosmology was in chaos, that everything we knew was wrong. This is the point at which it becomes essential to slow down and separate the genuine scientific tension from the noise of the headlines, because the truth, as is so often the case, is both more subtle and more interesting than the dramatic version. The Big Bang itself was never in danger. The fundamental picture of an expanding universe that began in a hot, dense state, that cooled and formed atoms, that released the microwave background we still detect, that forged the lightest elements in its first minutes, remains overwhelmingly well supported by an enormous body of evidence. No discovery of an early galaxy, however massive, threatens that foundation. What was challenged, and what remains genuinely uncertain, is something more specific and more delicate: the detailed timeline of how structure assembled within that expanding universe, the precise pace at which gas gathered, stars ignited, and galaxies grew. The Big Bang is the stage. The timeline of structure formation is the choreography of the dance performed upon it. It was the choreography, not the stage, that the new observations seemed to challenge, and even that challenge came wrapped in layers of caution, because the chain of reasoning that turns a faint smudge of infrared light into a confident statement about mass and age is long, and every link in that chain carries uncertainty. The very first question any careful scientist asked was whether these galaxies were truly as distant as they appeared. Estimating distance from the colors of a faint object alone, a method called photometric redshift, is powerful but imperfect. Sometimes a relatively nearby galaxy, heavily reddened by dust, can masquerade in its colors as a far more distant object. The dust absorbs blue light and lets red light through, mimicking the reddening that vast cosmic distance and expansion produce. A dusty nearby galaxy and a pristine distant one can, in the wrong light, look deceptively alike. This is why spectroscopy matters so much, and why the field held its breath waiting for follow-up observations. Spectroscopy spreads the light into its full spectrum and looks for specific fingerprints, particular features imprinted by particular atoms, that pin down the distance with far greater confidence than colors alone. When astronomers obtained spectra for some of these candidate galaxies, the results were illuminating in more ways than one. A number of the candidates were confirmed to be genuinely distant, genuinely early, exactly as the colors had suggested. But others turned out to be more complicated. Some appeared to be at lower redshifts than first estimated. Some showed signs that their light was dominated not purely by stars, but by something else entirely. That something else points toward one of the most fascinating possible resolutions to the puzzle. When astronomers estimate the mass of a galaxy from its brightness, they assume that the light comes from stars, and they translate the quantity of light into a quantity of stellar mass. But stars are not the only thing in the universe that shines. At the heart of many galaxies lurks a supermassive black hole, and when such a black hole is actively feeding, drawing in surrounding gas, that gas heats to tremendous temperatures and blazes with extraordinary brilliance before it crosses the point of no return. A feeding black hole can outshine all the stars of its host galaxy combined, and if some of the light from these early galaxies comes not from vast populations of stars, but from a single brilliantly feeding black hole at the center, then the inferred stellar masses would be dramatically overestimated. The galaxies would not contain as many stars as the Milky Way after all. They would simply contain a very bright and very hungry monster at their core. The mathematics become even more remarkable when you consider what the telescope actually found when it looked closely at many of these early, compact, intensely red objects. A whole new class of mysterious sources emerged from the deep surveys, objects so distinctive in their appearance that astronomers gave them their own informal name. They are small, they are compact, they glow with a deep red color, and so they came to be called, simply and vividly, the little red dots. These objects are among the strangest discoveries of the entire mission, and they sit right at the center of the puzzle of the early universe. They are abundant in the early cosmos, and rare or absent later, and their nature is still fiercely debated. Consider what these little red dots might be. One leading idea is that they are powered, at least in part, by rapidly growing black holes in the very young universe. Black holes feeding so voraciously that they shine like beacons across more than 13 billion years. If that is true, then some of the apparently impossible early galaxies are not overgrown collections of stars at all. They are the brilliant signatures of early black holes, and the mystery shifts from how galaxies grew so fast to how black holes grew so fast. That is no small mystery in itself, because growing a massive black hole also takes time, and finding enormous black holes in the very early universe poses its own deep puzzle. But it is a different puzzle, and it relieves some of the pressure on the timeline of galaxy growth, even as it deepens the mystery of black hole growth. This distinction matters enormously because it shows how a single surprising observation can branch into several possible explanations, each one leading down a different corridor of physics. Perhaps the early galaxies are exactly as massive as they first appeared, and the timeline of star formation needs revision. Perhaps much of their light comes from feeding black holes, and the stellar masses are overestimated, while the black hole masses pose a new and separate puzzle. Perhaps some of the candidates are nearer and dustier than they seemed, and the most extreme cases will dissolve under closer inspection. Perhaps the early universe formed stars far more efficiently than later epochs, converting a much larger fraction of available gas into stars. in a burst of cosmic productivity that has no parallel in the present day. Each of these possibilities is being investigated, tested, argued over and refined, and the honest answer to which one is correct is that nobody yet knows for certain. What is not in doubt is that the early universe was more active, more luminous, and more rapidly developing than the standard timeline comfortably predicted. The tension is genuine, even if its ultimate resolution remains open, and the very existence of that tension is a profound and beautiful thing. It is the sound of the universe pushing back against our expectations, refusing to be quite as tidy as our models wished it to be. There is a particular kind of intellectual joy in this, the joy of being surprised by reality, of discovering that the cosmos is stranger and richer than the story we had written for it. The greatest moments in science are not the moments when a theory is confirmed. They are the moments when a careful observation refuses to fit and forces us to think again. To appreciate how rare and significant such moments are, consider how rigid the standard model of cosmology had become before the new telescope opened its eye. It had succeeded so spectacularly, predicting the microwave background, the abundance of light elements, the large-scale distribution of galaxies, that it had earned a kind of quiet confidence, an assumption that the broad outlines of cosmic history were settled and only the details remained. The model rests on a small number of ingredients: ordinary matter, the kind that makes up stars and planets and people, which accounts for only a small fraction of the whole; a mysterious dark matter, which neither emits nor absorbs light, but whose gravity shapes the growth of structure; and a still more mysterious dark energy, which appears to be driving the expansion of the universe to accelerate. From these ingredients, and a handful of measured numbers, the model builds the entire history of the cosmos. And the model encodes, deep within its equations, a specific prediction for how quickly galaxies should grow. The dark matter gathers first, pulled together by gravity into invisible structures called halos, and the ordinary gas falls into those halos, cooling and condensing and forming stars. The rate at which the halos grow, and therefore the rate at which galaxies can form within them, is set by the cosmic ingredients and the expansion rate. Speed up galaxy formation too much, and you are implicitly saying that something about those ingredients, or about the early conditions, or about the physics of how gas turns into stars, is not what we assumed. The early galaxies that the telescope found are, in a sense, a message written in light, and the message reads, "The recipe may be incomplete." Now extend that calculation across the whole sweep of cosmic history, and the stakes of the puzzle come into focus. If the early universe formed structure faster than the standard model allows, the implications could ripple forward through all of cosmic time, touching everything from the nature of dark matter, to the value of the expansion rate, to the fundamental physics of the first moments. Or, alternatively, the puzzle might resolve into something far more local and specific, a matter of how efficiently early gas formed stars, or how much of the early light came from black holes, leaving the grand cosmic framework intact. The difference between these outcomes is the difference between a minor correction to a detail and a crack in the foundation, and at present, the field stands genuinely uncertain about which it will turn out to be. This is the disturbing and exhilarating reality of cosmology in this moment. We are living through one of those rare intervals when the universe has handed us a genuine surprise, a set of observations that do not quite fit, and we do not yet know whether the resolution will be modest or revolutionary. The galaxy whose light frames our journey tonight, glimpsed when the universe was only about 290 million years old, sits at the very frontier of this uncertainty. It is real, its light is undeniable, and its existence, so bright and so early, is one of the threads that, when pulled, might unravel a piece of the timeline we thought we had woven tight. To understand what could be unraveling and what might replace it, we have to descend into the deepest and strangest layer of the puzzle, into the question of what the early universe was actually made of, and whether the ingredients we counted are truly all there is. Understanding why the early universe might have grown its galaxies so quickly requires dismantling everything you think you know about how stars are born. In the modern nearby universe, Star formation is a slow and wasteful business. A great cloud of gas, given the chance to collapse under its own gravity, does not turn smoothly into stars. Instead, the first stars that form blaze with fierce radiation and explode as supernovae, and that radiation and those explosions blow much of the remaining gas back out, scattering it, heating it, preventing it from collapsing further. Star formation, in other words, tends to sabotage itself. A galaxy converts only a small fraction of its available gas into stars before its own newborn stars disrupt the process. This self-regulation is one of the reasons galaxies grow as slowly as they do, and it is built into the standard timeline. But there is no law of nature that guarantees the early universe behaved the same way. Consider what was different about the cosmos in its first few 100 million years. It was smaller, and therefore denser. The same amount of matter occupied far less space, so gas was packed more tightly, and gravity could gather it more easily and more quickly. The gas was nearly pristine, made almost entirely of hydrogen and helium, with almost none of the heavier elements that later generations of stars would forge. And those heavier elements matter, because they change how gas cools, how it fragments, and crucially, what kinds of stars form from it. In a universe with different gas, under different conditions, star formation might have proceeded along very different lines. Faster, more efficient, less self-limiting. This opens one of the most elegant possible explanations for the puzzle. Perhaps the early universe simply formed stars more efficiently than the present universe does. Perhaps a much larger fraction of the available gas was converted into stars before the disruptive feedback could shut the process down. If the early cosmos turned, say, a substantial fraction of its gas into stars, rather than the small fraction typical today, then the same amount of underlying matter could produce far more starlight, far sooner. The galaxies would appear unexpectedly bright and massive, not because the fundamental cosmic ingredients were wrong, but because the recipe for turning gas into stars ran hotter and faster in the early kitchen of the universe. This explanation has the great virtue of leaving the foundations of cosmology untouched, while still accounting for the surprising brightness. There is a second related idea that is stranger and more beautiful. It concerns the kinds of stars that formed in the early universe, and it rests on a property astronomers call the initial mass function, which is simply the distribution of how many stars form at each size. In the present universe, small stars are common, and large stars are rare. For every massive, brilliant, short-lived giant, there are many small, dim, long-lived dwarfs. But the early universe, with its pristine gas and its different cooling conditions, may have favoured the formation of much larger stars. If the first generations of stars were systematically more massive, then each one would have been far brighter, blazing with a luminosity out of all proportion to its mass. Consider what this would do to our measurements. When astronomers see a bright early galaxy and translate that brightness into a stellar mass, they assume a certain mix of star sizes, a certain relationship between how much light a population of stars produces and how much mass it contains. If the early universe was instead filled with unusually massive, unusually luminous stars, then a given amount of light would correspond to far less total mass than we assumed. The galaxies would appear massive, but they would in fact be lighter than they seem, their brilliance produced by a smaller number of exceptionally bright giants, rather than by a vast multitude of ordinary stars. This is the kind of subtle correction that could dissolve much of the tension without requiring any change to the deep architecture of the cosmos. The galaxies would not be too massive after all. We would simply have been misreading their light. These explanations are appealing precisely because they are conservative. They keep the standard model intact and locate the surprise in the messy, complicated physics of how gas becomes stars, a domain where we have always known our understanding to be incomplete. But not everyone is convinced that the surprise can be contained so neatly, and this is where the story descends into deeper and more speculative territory, into possibilities that, if true, would touch the foundations themselves. We should walk carefully here, because the further we go, the more uncertain the ground becomes, and the more important it is to remember that these are ideas under investigation, not established conclusions. The honest answer to most of the questions ahead is that nobody knows. The deepest possibilities involve the mysterious dark components of the universe, the dark matter and dark energy that together make up the overwhelming majority of everything, and which we understand only dimly. Dark matter, in the Standard Model, is assumed to be a particular kind of substance, cold and slow-moving, gathering gradually into halos that grow from small to large. But what if that assumption is not quite right? What if dark matter behaves somewhat differently than we have supposed, allowing structure to gather faster, or to form on different scales, in the early universe? There are versions of dark matter theory in which structure forms more quickly, and some researchers have wondered whether the surprisingly early galaxies might be a clue pointing towards such alternatives. It is a speculative idea, far from proven, but it illustrates how an unexpected observation in the distant past can reach all the way down to questions about the fundamental nature of matter. There is an even more provocative possibility, one that has captured the imagination of some researchers, involving objects called primordial black holes. The black holes we know about today formed from the collapse of massive stars, or grew over cosmic time at the centers of galaxies. But it is conceivable that black holes also formed in the very first instance of the universe, directly from the extreme densities of the early cosmos, before any star had ever shone. If such primordial black holes existed in significant numbers, they could have served as seeds, gravitational anchors around which gas gathered far earlier and far faster than the standard picture allows. They might explain both the surprisingly early galaxies and the surprisingly massive early black holes in a single stroke. This idea too remains speculative and contested, a thread that may lead somewhere profound or may unravel into nothing. But its very existence shows how the puzzle of the early galaxies reaches towards some of the most fundamental open questions in all of physics. Now consider a possibility more unsettling still, because it touches the number that has anchored this entire journey. We have spoken throughout of the universe being 13.8 billion years old, a number assembled with great care over more than a century. But what if that number is slightly wrong? What if the universe is somewhat older than we believe? Even a modest increase in the age of the cosmos would give structure more time to form, easing the tension of the early galaxies. This is not an idle fantasy. There is a genuine and unresolved discrepancy in modern cosmology, one that has nothing directly to do with the early galaxies, but that hovers over the whole field like a quiet alarm. It is called the Hubble tension, and it deserves to be understood because it is one of the most serious puzzles in physics today. The Hubble tension arises from two different ways of measuring how fast the universe is expanding, two methods that ought to agree and stubbornly do not. One method works outward from the early universe, using the precise pattern of the microwave background, the afterglow of the beginning, to calculate the expansion rate. The other method works inward from the nearby universe, measuring the actual distances and recession speeds of relatively close galaxies, building up a cosmic distance ladder rung by rung, much as Hubble himself did nearly a century ago, though with vastly greater precision. These two methods, the early universe method and the late universe method, give answers that disagree by a small but persistent amount, an amount too large to be explained away as mere measurement error. The universe seems to be expanding faster than the early universe calculation predicts. This distinction matters enormously because it hints that something in the Standard Model may be incomplete. The expansion rate connects directly to the age of the universe and to the rate at which structure forms. If the true expansion history differs from what the Standard Model assumes, then the timeline itself could shift, and the early galaxies might find a little more room to exist. Some researchers have proposed exotic ideas to resolve the Hubble tension, including a notion called early dark energy, a hypothetical extra push present in the very young universe that faded away as the cosmos matured. Such ideas are speculative and far from confirmed, and they were not invented to explain the early galaxies. But it is striking, and perhaps significant, that the universe seems to be sending us more than one signal that the early epochs may not be quite as our standard story describes. The early galaxies are one signal. The Hubble tension is another. Whether they are connected, whether they point toward a single deeper truth, nobody yet knows. To appreciate how delicate this all is, consider the difference between a model being slightly adjusted and a model being overthrown. Science does not usually proceed by sudden revolutions in which everything old is swept away. Far more often, it proceeds by refinement, by the addition of new ingredients to an existing recipe, by the adjustment of numbers and the inclusion of effects previously thought negligible. The most likely outcome of the early galaxy puzzle is not that the Big Bang will be abandoned, nor that cosmology will collapse into chaos, but that the standard model will be enriched, made more complete, its account of the early universe deepened and corrected. The headlines that proclaimed the universe broken were, almost certainly, overstating the case. The universe is not broken. Our understanding of it is simply and wonderfully incomplete. And yet there remains the tantalizing possibility, faint but not zero, that the puzzle is pointing towards something larger, some genuinely new piece of physics that we have not yet grasped. This is the possibility that keeps cosmologists awake, the small but real chance that the surprisingly early galaxies are not a minor wrinkle to be smoothed out, but a thread that, when fully pulled, reveals a tapestry different from the one we thought we were weaving. History offers precedents on both sides. Many anomalies have dissolved into mundane explanations once the data improve, but a few, a precious few, have cracked open into revolutions, into relativity, into quantum mechanics, into the expanding universe itself. There is no way to know in advance which kind of anomaly the early galaxies will turn out to be. That uncertainty is not a weakness of science, it is the living edge of it. What makes this moment so compelling is that the question is genuinely open and actively being resolved, night after night, as the great telescope continues to gather light from the edge of time. Every new spectrum, every confirmed redshift, every careful measurement of an early galaxy's properties adds a piece to the puzzle. Some pieces will support the conservative explanations, the efficient star formation, the unusually massive early stars, the misread light. Other pieces may push toward the more radical possibilities, the modified dark matter, the primordial seeds, the adjusted timeline. The picture is assembling slowly, in real time in our own era, and we are among the first humans in history privileged to watch it form. The early universe, long hidden behind the cosmic dark ages, is finally yielding its secrets, and the secrets are stranger than we expected. There is something deeply humbling in all of this, and it is worth letting that humility settle before we go further. For decades we believed we understood the broad shape of cosmic history, the orderly progression from the hot beginning through the dark ages into the slow assembly of structure. We built our models, ran our simulations, and grew confident. And then we built a better eye and pointed it at the deepest past, and the past surprised us. It is a reminder, written across 13 billion years, that the universe is under no obligation to match our expectations, that our most cherished models are always provisional, and that the cosmos retains the power to astonish us, no matter how clever we believe ourselves to have become. The galaxy at the edge of time is not just an object, it is a teacher, and its lesson is the oldest and most valuable in all of science, that we know less than we think, and that this is precisely what makes the universe worth exploring. There is a limit to how far back even the greatest telescope can ever see, and understanding that limit reveals just how close to the edge of the possible these early galaxies truly lie. We have spoken of recombination, the moment about 380,000 years after the beginning when the universe became transparent and released the light we now detect as the microwave background. That moment is a wall. It is the earliest snapshot of the cosmos that ordinary light can ever bring us, because before it, the universe was opaque, and no telescope, however powerful, can see through an opaque fog. Beyond that wall lies the true infancy of the universe, the first minutes and seconds, accessible only through indirect clues and theoretical reconstruction. The microwave background is the oldest light. There is no older photograph to be had. But between that wall of recombination and the formation of the first galaxies lies a vast and mysterious gulf, the cosmic dark ages and the cosmic dawn, an era of hundreds of millions of years during which the universe transformed from a smooth dark sea of neutral gas into a cosmos lit by the first stars and galaxies. This is the frontier. This is the era the great telescope is now probing, reaching back further than any instrument before it, catching the first faint structures as they emerged from the darkness. The galaxy at redshift 14, glimpsed when the universe was only about 290 million years old, sits deep within this frontier, near the very edge of what current technology can reach. To see it at all is an extraordinary achievement. To find it so bright and so substantial is the surprise that animates this entire story. Consider how thin the margin is. The telescope is detecting these galaxies near the limit of its sensitivity, gathering only a handful of photons from objects so distant that their light has been stretched far into the infrared and dimmed by the immense journey. Each detection is hard-won, the product of long exposures and careful analysis. And yet, against all the difficulty, the early universe keeps revealing itself to be more populated and more luminous than the timeline predicted. If the very edge of the observable past is already this surprising, one cannot help but wonder what lies just beyond it, in the era the telescope cannot quite reach, where the very first stars and the very first structures were taking shape in the dark. The frontier is not the end of the mystery. It is the doorway to a deeper one. To probe that deeper era, astronomers are turning to methods that do not rely on ordinary light at all. There is a particular signal, a faint radio whisper emitted by neutral hydrogen gas, that in principle could allow us to map the dark ages and the cosmic dawn directly, charting how the first light from the first stars rippled out into the surrounding gas and slowly transformed it. This signal is extraordinarily difficult to detect, buried beneath enormous interference, and capturing it cleanly may require radio telescopes built in the radio silence of the far side of the moon, shielded from the noise of Earth. It is one of the great ambitions of the coming decades, a way to read the chapters of cosmic history that lie before the first galaxies, in the long darkness between recombination and dawn. If it succeeds, it will let us watch the cosmic dawn unfold in detail, and it may finally tell us whether structure truly formed faster than we believed. There are other approaches too, each one a different way of listening to the early universe. Future space telescopes, larger and more sensitive still, are being designed to push the frontier further, to gather more light from the earliest galaxies and to measure their properties with greater precision. Gravitational wave observatories, which detect ripples in the fabric of space itself rather than light, may one day sense the mergers of the first massive black holes, offering a completely independent window onto the early cosmos. And the great surveys continue, night after night, accumulating ever larger samples of early galaxies, transforming what began as a handful of startling outliers into a population that can be studied statistically, its properties mapped, its surprises pinned down. The puzzle of the early galaxies will not be solved by a single observation. It will be solved, if it is solved, by the slow convergence of many independent lines of evidence. This is the patient and methodical reality of how the deepest questions are answered. Not in a flash, but in a gradual tightening of the web of evidence until the truth, whatever it is, has nowhere left to hide. And the truth that is emerging, even now, even before the puzzle is fully resolved, is that the early universe was a place of astonishing creativity and speed. Whatever the ultimate explanation, whether efficient star formation, or unusually massive early stars, or feeding black holes, or some deeper revision of cosmic physics, the conclusion is the same. The cosmos got to work building structure earlier and more vigorously than we imagined. The dawn was brighter than we thought. The first chapters were fuller than we wrote them. There is a particular thread within this story that deepens the mystery further, and it concerns those black holes we touched on earlier. the ones that may be powering the little red dots and inflating the apparent masses of early galaxies. Even setting aside the question of starlight, the mere existence of massive black holes in the very early universe is a profound puzzle in its own right. A black hole grows by feeding, and there is a maximum rate at which it can feed, set by the balance between the inward pull of gravity and the outward pressure of the radiation produced by the infalling matter. Feed too fast, and the radiation blows the incoming gas away, throttling the growth. This limit means that growing a truly massive black hole takes time, a great deal of time, starting from a modest seed. And yet the early universe appears to contain black holes of surprising heft, present when the cosmos was only a few 100 million years old, far too soon for them to have grown from ordinary stellar seeds at the standard rate. How did they get so big so fast? Here again the field offers several possibilities, none yet confirmed. Perhaps the first black hole seeds were not the remnants of individual stars, but were born already large, from the direct collapse of enormous clouds of pristine gas, skipping the slow stellar stage entirely. Perhaps black holes in the early universe were able to feed faster than the usual limit allows, in brief episodes of extraordinary growth. Perhaps, as some have speculated, the seeds were primordial, formed in the first instance of the cosmos. The mystery of the early black holes runs parallel to the mystery of the early galaxies, two puzzles braided together, each one straining against the comfortable timeline, each one demanding that the early universe was more productive than we believed. What this means for a person, sitting quietly in the dark and contemplating it, is something worth dwelling on. We tend to imagine the early universe as a simple place, a smooth and featureless beginning from which complexity slowly emerged. But the evidence is telling us something almost opposite. The early universe was a place of fierce and rapid creation, of stars igniting in great bursts, of black holes growing with startling speed, of galaxies assembling far faster than our models prepared us for. The dawn of the cosmos was not a gentle, gradual brightening. It was, in places, a sudden blaze. And the light from that blaze, after travelling for more than 13 billion years across an expanding universe, is arriving now, in our era, falling onto a golden mirror in the cold 1,000,000 miles from Earth, carrying a message we are only beginning to decode. Consider the strange intimacy of this. The photons striking that mirror tonight began their journey before the Earth existed, before the Sun and its planets had condensed from their parent cloud, before there was any such thing as a rock or an ocean or a living cell anywhere in the cosmos, as far as we know. They crossed an expanding universe for more than 13 billion years, untouched, undisturbed, carrying their ancient information faithfully across an almost unimaginable gulf of time and space. And at the end of that journey, they encountered, of all things, an instrument built by a particular species of curious primate on a small wet planet, a species that had only learned to read the sky in the last sliver of cosmic time. The light waited 13 billion years to be understood. We have been capable of understanding it for only a handful of decades. This is the chilling and beautiful reality of cosmic observation. We are catching light older than almost everything, and we are catching it just barely in time, at the very edge of its visibility, after it has been stretched and dimmed nearly to nothing by the expansion of the universe. A little further in time, a little more expansion, and these earliest galaxies will redshift beyond even our best instruments, fading into an infrared too faint and too stretched to capture. The window onto the cosmic dawn is open now, in our era, but it is not a window that stays open forever in the same form. The universe is still expanding, still stretching the ancient light, still carrying the earliest galaxies further into invisibility. We are looking back at the dawn through a window that the universe itself is slowly closing. To appreciate how remarkable our position is, consider what an observer in the far future would see. Trillions of years from now, if any observers remain, the accelerating expansion of the universe will have carried all the distant galaxies beyond the horizon of visibility. The night sky of the far future will be empty of all but the nearest galaxies, and an astronomer of that era, looking outward, would find no evidence of the expansion, no distant galaxies rushing away, no microwave background, no clue that the universe had a beginning at all. They would conclude, reasonably and wrongly, that they lived in a small, static, eternal cosmos. The evidence of the Big Bang, the evidence of the early galaxies, the evidence of cosmic history itself, is visible only during a particular window of cosmic time. And we happen to live within that window. We are among the few who can ever know the true story. This distinction matters enormously because it transforms our moment from an ordinary one into a privileged one. We are not merely curious creatures peering at the sky. We are creatures who happen to exist during the brief cosmic epoch when the deep past is still legible, when the light of the first galaxies has not yet faded beyond reach, when the afterglow of the beginning still hums faintly in our instruments. To be alive now, and to be capable of understanding what we see, is to occupy a rare and fleeting vantage point in the long history of the universe. The early galaxy at the edge of time is visible to us, and to almost no one else who will ever exist. We are the witnesses, and the witnessing will not last forever. And here is the deeper layer beneath even that, the thread that connects the cold abstraction of distant galaxies to the warm fact of your own existence. The early galaxies we are studying are not separate from us. They are our ancestors. The first stars and the first galaxies forged the first heavy elements, the carbon and oxygen and iron and all the rest. Elements that did not exist in the pristine hydrogen and helium of the beginning. Those elements were scattered into space when the first stars died, and they enriched the gas from which later stars formed. And those later stars forged still more, and the cycle repeated across billions of years, building up the chemical richness of the cosmos generation by generation. The atoms in your body, the calcium in your bones, the iron in your blood, the oxygen you are breathing in this very moment, were forged in the hearts of stars and scattered by their deaths across cosmic time. The story of the early galaxies is the opening chapter of the story that ends in you. So when we study the galaxy at the edge of time, when we puzzle over how it grew so fast and shone so bright, we are not studying something alien and remote. We are studying the deep origins of the very atoms that compose us. The rapid, creative, surprising early universe that the telescope is revealing is the universe that, across 13 billion years, eventually produced the conditions for a small planet to form, for chemistry to grow complex, for life to emerge, and at last for a creature to look up, to build a golden mirror, and to catch the ancient light of its own beginning. The mystery of the early galaxies is, in the deepest sense, a mystery about ourselves. We are the universe's way of looking back at its own dawn. This is the unsettling reality of standing at the frontier of knowledge. The map of cosmic history that we carried into this era, so confident and so detailed, has revealed a region where the territory does not match the chart, and the honest scientist does not paper over that mismatch. They mark it plainly, with a question, and they keep exploring. The early universe is more luminous, more rapidly developing, more populated than we expected, and the precise reason remains genuinely unknown. We have several candidate explanations, each one plausible, each one partial, none yet decisive. We are in the uncomfortable and exhilarating middle of a real scientific puzzle, the kind that may take a decade or more to fully resolve. Consider what it feels like to hold that uncertainty. For a person who craves tidy answers, it can be disquieting, even vertiginous, to learn that the experts do not yet know, that the timeline of the universe contains a chapter we are still struggling to read. But there is another way to hold it, a way that turns the disquiet into wonder. The fact that we do not yet understand the early galaxies is not a failure, it is a frontier. It is the precise location where the known meets the unknown, the place where discovery happens. Every great advance in our understanding of the universe began exactly here, in a region where the old map failed and a careful observer noticed. The puzzle of the early galaxies is not a hole in our knowledge to be ashamed of. It is an invitation, written in ancient light, to look closer and think harder. And the thinking is happening right now in offices and observatories around the world as researchers pore over spectra, refine their models, run new simulations, and argue productively and passionately about what the early universe is telling us. Some are convinced the tension will dissolve into the conventional physics of star formation. Others suspect it points towards something deeper. The debate itself is the engine of progress, the friction that grinds raw observation into refined understanding. There is no consensus yet, and that absence of consensus is not a weakness. It is the sign of a living science, working at the edge of what it knows, on a question that genuinely matters. To appreciate how this kind of puzzle resolves, it helps to remember that the universe has surprised us before, many times, and that each surprise, once understood, enlarged us rather than diminished us. When the spectral lines of distant nebulae first revealed their redshifts, no one knew they were watching the expansion of the universe. When a faint hiss refused to leave a radio antenna in New Jersey, no one immediately grasped that they were hearing the afterglow of the beginning. When the expansion of the universe was found to be accelerating, in the late 1990s, it forced the introduction of dark energy, a mysterious component we still do not understand, comprising most of the cosmos. Each of these surprises began as an anomaly, a result that did not fit, and each one in time deepened our picture of reality. The early galaxies stand in that same lineage. They are the latest in a long line of cosmic surprises, and like the others, they will eventually teach us something true. What that lesson will be, we cannot yet say. Perhaps it will be modest, a refinement of how we understand star formation in pristine gas, a correction to the recipe that leaves the grand framework intact. Perhaps it will be more significant, a revision to the timeline of structure formation, a new appreciation of how fast the early cosmos could build. Or perhaps, in the most dramatic and least likely outcome, it will point toward genuinely new physics, toward a dark matter that behaves differently than we thought, or an early universe with an extra ingredient we have not yet identified, or a cosmic history subtly different from the one we reconstructed. The range of possibilities is itself a kind of beauty. The universe has left the answer open and invited us to find it. There is a particular emotional texture to living through such a moment, and it is worth naming it plainly. It is the feeling of standing before something vast and incompletely understood, and feeling simultaneously the thrill of the mystery and the vertigo of our own smallness. The early galaxies are real, and they are strange, and we do not fully understand them, and they existed 13 billion years before we were born to wonder about them. Contemplating them, a person feels at once magnified and diminished. Magnified because we are the creatures who can reach across 13 billion years and catch this ancient light and puzzle over its meaning. Diminished because the puzzle is so much larger than we are, the timescales so vast, the distances so incomprehensible, that our own brief lives seem to shrink to a single point against the immensity. And yet that diminishment, strangely, does not feel like despair. There is a comfort hidden inside the smallness, a comfort that the great contemplatives of every age have known. When you truly grasp the scale of the cosmos, when you feel in your body the 13 billion years and the unimaginable distances and the slow patient stretching of ancient light, your own worries, your small daily anxieties, do not vanish, but they find their proportion. They settle into a larger frame. The universe is enormous and old and strange, and you are a brief, warm, conscious flicker within it, capable of contemplating the whole. That is not a small thing to be. It may in fact be one of the most extraordinary things the universe has ever produced. So as the great telescope continues its patient work, gathering light from the edge of time, refining our understanding of the dawn of the cosmos, we are left with a puzzle that is not yet solved, and a wonder that does not require solving. The galaxy at redshift 14 exists. It was bright and substantial when the universe was very young. It presses against our timeline, and we do not yet fully know why. And in that not yet knowing lies the deepest invitation the universe ever extends to us. The invitation to keep looking, to keep wondering, to keep reaching across the abyss of time toward an understanding that always recedes a little further the closer we approach. The dawn of the cosmos is still revealing itself, and we are still learning to read its light. To feel the true strangeness of what we are seeing, it helps to lay the history of the universe across a single year, a trick that astronomers and teachers have used for generations, because the human mind cannot grasp 13 billion years directly. So imagine the entire age of the cosmos compressed into one calendar year. The beginning happens in the first instant of the 1st of January. On this scale, each month represents a little more than 1 billion years, and each day represents nearly 38 million years. The early galaxies we have been discussing, glimpsed when the universe was only 200 to 300 million years old, formed within the first week of January, when the cosmic year had barely begun. The first faint structures emerged, while the calendar still read the first days of the first month. Now consider where everything you have ever known falls on that same calendar. The Sun and the Earth do not form until early September, more than 8 months into the cosmic year. The first simple life on Earth appears later that month. For the entire autumn, life remains microscopic, single cells drifting in ancient seas. Complex animals do not appear until December. The dinosaurs arise and then vanish in the last week of the cosmic year. And all of recorded human history, every civilization, every invention, every life ever lived since the first written word, occupies the final few seconds before midnight on the 31st of December. The great telescope, the discovery of the early galaxies, this very moment of contemplation, all of it happens in the last fraction of the last second of the cosmic year. We are creatures of the final instant, looking back at the first week. This distinction matters enormously, because it reframes the early galaxies not as remote curiosities, but as the deep foundation upon which everything else was built. When those first galaxies blazed into existence in the cosmic first week, there was no Earth, no Sun, no possibility yet of anything like us. And yet the work they did, the forging of the first heavy elements, the seeding of the gas that would form later generations of stars, made everything that followed possible. The entire towering structure of cosmic history, all the way up to the warm conscious moment you are living right now, rests upon the foundation laid in those first surprising, luminous, rapidly forming early galaxies. They are the bedrock. And the bedrock, it turns out, was poured faster than we knew. Consider what this means for a person trying to feel their place in the story. You are not separate from the early universe. You are its continuation. The hydrogen in the water you drink is primordial, forged in the first minutes after the beginning, older than any star. The heavier atoms in your body were assembled later, in the furnaces of stars that lived and died across billions of years, the earliest of them perhaps in galaxies like the ones the telescope is now finding at the edge of time. When you breathe, you are breathing oxygen that was created in stellar cores and scattered across the cosmos by stellar deaths. When your heart beats, it pumps blood made red by iron, forged in the violence of dying stars. You are, quite literally, assembled from the ash of ancient cosmic fires, fires that began burning in the universe's first week. To contemplate the early galaxies is to contemplate your own deepest ancestry. There is a kind of vertigo in holding all of this at once, and it is worth letting that vertigo wash through you slowly, the way a tide moves up a beach. The numbers are too large for intuition. 13 billion years. Hundreds of billions of stars in a single galaxy. Hundreds of billions of galaxies in the observable universe. Distances so vast that light, the fastest thing there is, takes billions of years to cross them. The mind reaches for these quantities and finds no handhold, no familiar scale to grip. And this failure of intuition is not a flaw in you. It is the honest response of a brain that evolved to track the movements of animals and the changing of seasons, suddenly confronted with the architecture of the cosmos. The wonder is not that we struggle to grasp these scales. The wonder is that we can approach them at all. Ask anyone to imagine the size of the universe, and they will reach for the largest thing they know, and they will fall hopelessly short. That is the nature of cosmic scale. It does not merely exceed our experience. It exceeds our capacity to imagine our experience exceeded. When astronomers say a galaxy lies 13 billion light-years away, the words are precise, but the reality behind them cannot be pictured, only gestured at. We build comparisons, scaled models, calendars compressed into a year, ping-pong balls standing in for stars, precisely because the raw truth resists direct comprehension. The comparisons are not the truth. They are ladders we build to climb partway toward a truth that towers always above us. And yet, partway is far enough to feel the awe. Here is the problem that has run quietly beneath this entire journey, the deepest version of the puzzle. We have built a magnificent model of the cosmos, and that model works astonishingly well across an enormous range of observations. It predicts the afterglow of the beginning. It accounts for the abundance of the lightest elements. It describes the large-scale distribution of galaxies across the sky with remarkable accuracy. And yet, woven through this triumphant model, there are threads that do not quite lie flat. The expansion rate measured two ways that refuse to agree. The early galaxies that formed faster than the timeline predicted. The mysterious dark matter and dark energy that together comprise most of the universe and that we do not understand at all. The model is the best description of reality we have ever constructed, and it is also, demonstrably, incomplete. To sit with that combination, magnificent success alongside genuine incompleteness, is to sit with the actual condition of science, stripped of the false certainty that sometimes gets draped over it. We do not have the final theory of the cosmos. We have an extraordinarily good approximation, riddled with deep and fascinating unknowns. The early galaxies are one of those unknowns, a place where the approximation strains, a clue that there is more to learn. And the appropriate response to such a clue is neither panic nor dismissal, but patient, careful, sustained attention. The universe has posed a question. We are working out the answer. It may take years. It may take a generation. The light will keep arriving, and we will keep learning to read it. What comes next will fundamentally alter how you think about the relationship between knowledge and mystery, because the two are not opposites. The more we learn about the universe, the larger the frontier of the unknown becomes, not smaller. Every answer opens new questions. When we learned the universe was expanding, we had to ask what it was expanding from, and we discovered the beginning. When we discovered the beginning, we had to ask what the early universe was like, and we built telescopes to see it. When we saw it, it surprised us, and now we must ask why. Knowledge does not shrink the unknown. It illuminates its edges, revealing how much vaster it is than we had supposed. The early galaxies are a perfect emblem of this. We reached further into the past than ever before, and what we found was not a tidy confirmation, but a fresh and profound mystery. And so we arrive, by the long road of light and time and patient reasoning, at the place where the science gives way to something older and deeper, the place where contemplating the cosmos becomes contemplating ourselves. The galaxy at the edge of time, bright and early and strange, has carried us back to the dawn of everything, and in doing so it has carried us inward, toward the most basic questions a conscious being can ask. What does it mean to be a brief, warm, thinking thing in a cosmos this vast and this old? What does it mean to understand, even partially, a universe that does not need us and did not make us on purpose? What does it mean to be the matter of the cosmos, briefly awake, looking back at its own beginning? These questions have no equations, they have no observations that will settle them, but they are, perhaps, the truest reason we look up at all. There is a silence in the deep universe that is difficult to describe and important to understand. The space between the galaxies is the emptiest emptiness imaginable, vast stretches where a single atom might drift alone for great distances, where the temperature has fallen to a few degrees above absolute zero. where the light of even the nearest galaxy is a faint and ancient whisper. The early galaxy at the edge of time exists within that silence, separated from us by billions of light years of nearly perfect emptiness. The universe is, overwhelmingly, a place of cold and dark and distance. The warm, bright, crowded conditions we take for granted on the surface of a small planet are not the cosmic norm. They are a rare and precious exception, an island of warmth in an ocean of indifferent cold. To appreciate how rare that warmth is, consider the journey the ancient light has taken to reach us. It crossed billions of light years of near total emptiness, untouched, undisturbed, because there was almost nothing out there to touch or disturb it. The cosmos is mostly void. The galaxies, for all their grandeur, are scattered through that void like rare islands across an impossibly wide sea, and between them lies a darkness so complete and so cold that it makes the deepest night on Earth seem warm and bright by comparison. This is the true backdrop of existence, a vast, cold, silent, expanding emptiness, dotted here and there with islands of light, on one of which, on one small world, conditions happen to allow the impossible thing called life. And yet, here is what most people get wrong about this cosmic emptiness. They assume that the vastness and the cold and the indifference of the universe must mean that our small warm existence is meaningless, a fluke, a trivial accident in an uncaring void. But that conclusion does not follow from the facts. The universe is indifferent, yes. It did not arrange itself for our benefit. It does not know we are here, but within that indifferent vastness, against all the odds, something extraordinary occurred. Matter organized itself into stars. Stars forged the elements. Those elements assembled, on at least one world, into structures complex enough to be aware, to wonder, to look back across 13 billion years and ask how it all began. The indifference of the universe does not diminish that achievement, it magnifies it. We are the unlikely warmth in the cold, the rare light in the dark, the brief awareness in the long silence. That is not nothing. That may be everything. The early galaxies, in their surprising brightness, deepen this sense of improbable wonder. The cosmos got to work building structure faster and more vigorously than we knew, lighting its first fires earlier than our timeline predicted, beginning the long chain of creation that would eventually lead to us with a speed that still puzzles the experts. We do not yet know exactly why, but we know that it happened, and we know that we are its distant consequence, and we know that we are, as far as we have yet discovered, the only part of the universe capable of knowing any of this at all. The dawn was brighter than we thought, and the brightness, in some long and winding way, eventually became us. So let the weight of it settle, here in the quiet, as the ancient light continues to fall on a golden mirror a million miles away. A galaxy shone at the edge of time, brighter and earlier than it should have, and its light has travelled across the entire age of the universe to reach an instrument built by creatures made of stardust on a small blue world. We do not fully understand what we are seeing. The timeline strains, the mystery is real, but the wonder is realer still, and it asks nothing of us except that we keep looking, keep wondering, and keep our small warm awareness turned toward the vast cold beautiful cosmos that, against all the odds, produced us. It is worth returning, one last time, to the human beings who made all of this possible, because the story of the early galaxies is also a story about a long chain of patient observers, each one handing a piece of understanding to the next. The chain stretches back further than most people realize, and it includes names that history has not always treated kindly. Consider Henrietta Swan Leavitt, who worked at the Harvard College Observatory in the early years of the 20th century, in an era when women in astronomy were employed to measure and catalogue the brightness of stars on photographic plates, painstaking work for low pay, often without recognition. Studying a particular class of pulsing stars, she discovered a relationship between how brightly they shone and how long they took to pulse. A relationship that turned these stars into reliable cosmic measuring sticks. That single discovery became the first rung of the cosmic distance ladder, the method by which astronomers gauge the distances to faraway galaxies. Without Leavitt's pulsing stars, Edwin Hubble could never have measured the distances that revealed the expansion of the universe. Without that expansion, there would have been no path to the Big Bang, no understanding of cosmic history, no framework within which to recognize the early galaxies as surprising at all. A quiet woman measuring stars on glass plates laid the foundation for everything that followed, and she died before the full significance of her work was widely understood. This distinction matters enormously because it reminds us that the great discoveries are never the work of a single mind in a single flash. They are the slow accumulation of many careful contributions, most of them made by people who never lived to see where their work would lead. To appreciate how the distances themselves defy intuition, consider a single concrete comparison, the kind that makes the abstract briefly graspable. If you could shrink the entire Milky Way galaxy, all 100 billion of its stars, down to the size of a dinner plate, then the nearest large galaxy to our own, the Andromeda Galaxy, would be another dinner plate sitting only a short distance away, a few feet across the table. But the early galaxy at the edge of time, on that same scale, would lie far beyond the room, beyond the building, beyond the city, at a distance that the dinner plate comparison cannot even contain. The light from it would have left when the dinner plate of our galaxy did not yet exist, when there was only scattered gas where the plate would someday form. The scales of distance and time fold into one another until the comparison itself breaks down, and we are left again at the edge of what the mind can hold. If you could somehow stand beside that early galaxy at the moment its light departed, and look around, you would find a universe profoundly unlike our own. The sky would not be the deep black we know, scattered with distant stars. It would be closer, smaller, the galaxies packed nearer together because the universe itself was so much smaller then. The light would be different, the gas would be more pristine. The great cosmic web of structure would be only beginning to take shape. And if you tried to find, anywhere in that young cosmos, a world like Earth, a planet of rock and water and air, you would search in vain. The heavy elements that rocky planets require had barely begun to be forged. The universe of the early galaxies was a universe before planets, before any possibility of life as we know it, a universe still assembling the raw materials from which worlds and creatures would eventually be made. This is the deeper meaning of the surprise the telescope has handed us. When we find galaxies forming faster and shining brighter than expected in that ancient era, we are learning that the assembly of those raw materials, the forging of the elements, the building of cosmic structure, began earlier and proceeded faster than we believed. The cosmic head start was greater than we knew, and a greater head start means that the long chain of events leading to planets, to chemistry, to life, to awareness, may have been set in motion sooner than our timeline suggested. The early galaxies are not just an abstract puzzle about distant light. They are a clue about the deep tempo of creation, about how quickly the universe got down to the business of building the conditions for everything that would follow, including us. And still, beneath all of this, the honest uncertainty remains, and it would be a disservice to pretend otherwise. We do not yet know whether the early galaxies are as massive as they first appeared, or whether their light is partly the glow of feeding black holes. We do not know whether the early universe formed stars with unusual efficiency, or whether it favored unusually massive stars, or whether something deeper in the physics of the cosmos is at work. We do not know whether the puzzle of the early galaxies connects to the puzzle of the disagreeing expansion measurements, or whether they are separate mysteries that merely happen to coexist. The map has a region marked unknown, and the cartographers are still surveying it, and there is no shame in saying so. The honest answer to many of the deepest questions is that nobody knows, not yet, and the work of finding out is ongoing, in our own time, in front of our eyes. What we can say is that the great telescope has opened a window onto the dawn of the cosmos wider and clearer than any before it, and that what we see through that window is more surprising, more luminous, and more rapidly alive than we expected. The early universe was not the dim and sluggish place our timeline described. It was, in its first chapters, a place of remarkable creative force, lighting its fires early, building its structures fast, beginning the long work that would end, billions of years later, in a conscious creature contemplating its own origins. The dawn was brighter than we thought. That much, at least, the ancient light has made clear. The why of it, the full explanation, we are still patiently, carefully working out, and we may be working it out for a long time yet. There is a common picture of the beginning that almost everyone carries, and understanding why it is wrong reveals something deep about the early galaxies. Ask most people to imagine the Big Bang, and they will picture an explosion, a single point in the darkness erupting outward, hurling matter into a pre-existing empty space. That picture is wrong. Not slightly wrong, fundamentally wrong. The Big Bang was not an explosion in space. It was an expansion of space itself. There was no pre-existing void for the universe to expand into. Space, and time along with it, came into being and began stretching, everywhere at once. The beginning did not happen at a particular place, because every place was, in that first instant, the same place. The Big Bang happened everywhere. This misconception persists because our minds are built to imagine explosions, and they are not built to imagine space itself stretching. We have all seen fireworks burst outward into the sky. None of us has ever seen the sky itself swell and grow. So we reach for the familiar image, and the familiar image leads us astray. The galaxies are not flying apart through space like shrapnel from a blast. They are being carried apart by the expansion of the space between them, like spots painted on the surface of a balloon that drift away from one another as the balloon inflates, each spot staying fixed on the rubber while the rubber itself grows. The galaxies are the spots, space is the rubber, the universe is the inflation. This distinction matters enormously because it changes how we understand the early galaxy at the edge of time. When we say its light has travelled for more than 13 billion years, we do not mean it travelled across a fixed distance. We mean it travelled across a distance that was itself stretching the entire way, growing beneath the light like a road extending as you walk along it. The light left a galaxy that was, at the time, far closer to the matter that would become us than it is now. As the light journeyed, the space it crossed expanded, carrying its source ever further away, stretching the light itself toward the red and the infrared. By the time the light arrives at the golden mirror, the galaxy that emitted it has been carried to a distance far greater than the light's travel time alone would imply. This is why the observable universe can be more than 90 billion light-years across, even though it is only 13.8 billion years old. The space grew while the light was in transit. Now consider what the early galaxies actually did to the universe around them, because their effect was profound, and it connects directly to the mystery of their abundance. We have spoken of the cosmic dark ages, the long era of neutral hydrogen gas drifting unlit through an expanding cosmos. That neutral gas was, in a sense, a fog. Ultraviolet light cannot easily pass through neutral hydrogen, because the hydrogen absorbs it. So even as the first stars and galaxies began to shine, the universe remained partly veiled, its early light struggling against the surrounding neutral gas. And then, gradually, the first galaxies began to change their surroundings. The intense ultraviolet radiation pouring out of their young hot stars began to strip the electrons from the neutral hydrogen, ionizing it, splitting the atoms back into charged particles. This process is called reionization, and it transformed the universe. Reionization was the moment the cosmic fog finally cleared for good, the moment the universe became fully transparent to ultraviolet light, the moment the Dark Ages truly ended. It did not happen all at once. It happened in patches, as bubbles of ionized gas grew around the first galaxies, expanding and merging like clearings spreading through a forest, until at last the bubbles overlapped, and the entire universe was ionized and transparent. Astronomers estimate that this great clearing was largely complete by the time the universe was about 1 billion years old. And here is where the early galaxies become essential, because it was their radiation, the combined ultraviolet output of the first generations of stars and galaxies that powered reionization. The galaxies did not merely exist in the early universe, they remade it. They lit the fog and burned it away. The mathematics become even more striking when you connect this to the surprising abundance of bright early galaxies. For decades, astronomers struggled to understand exactly how reionization was accomplished, because it was not obvious that the early universe contained enough sources of ultraviolet light to do the job. There seemed to be a shortage of photons, a deficit between what was needed to clear the fog and what the known early galaxies could supply. But if the early universe was richer in bright galaxies than the old timeline predicted, if the cosmic dawn blazed earlier and harder than we believed, then perhaps that deficit resolves itself. Perhaps the surprising abundance of luminous early galaxies is exactly what was needed to reionize the universe on schedule. The puzzle of the bright early galaxies and the puzzle of how reionization happened may be two faces of the same underlying truth. The early universe was simply more luminous than we thought. This is the kind of connection that gives scientists hope that the pieces will eventually fit together into a coherent new picture, even if the picture differs in its details from the one we carried before. An unexpected abundance of bright early galaxies is troubling in isolation. But if that same abundance helps explain how the cosmic fog was cleared, then the surprise begins to look less like a contradiction and more like a clue. A thread that, followed carefully, leads toward a richer and more complete understanding. The early galaxies are not only a problem to be solved, they may also be part of the solution to other long-standing problems. This is how science heals itself after a surprise. The anomaly that breaks one part of the picture often turns out to repair another, and slowly, the new picture assembles, more accurate than the old. Consider, too, how rapidly our knowledge of this era has changed in just a few short years. Before the Great Telescope opened its eye, the most distant galaxy ever confirmed sat at a redshift just above 11, a lonely record holder at the very edge of what the older instruments could reach. Within a single year of the new telescope beginning its work, that record had been broken again and again, pushed to redshift 12, then 13, then beyond 14, each new record extending our reach deeper into the cosmic dawn. This is a pace of discovery almost without precedent in the study of the early universe. A frontier that had crept forward slowly for decades suddenly leapt ahead, and the galaxies we found at that new frontier were not the faint, struggling whispers we expected. They were brighter, more substantial, more developed. The speed of the discoveries mirrors the speed of the early universe itself, as though the cosmos, having built its first galaxies in a hurry, was now revealing them to us in a hurry as well. We are living through a rare burst of cosmic understanding, and the dawn keeps yielding its secrets faster than we can fully absorb them. And yet, even as some pieces fall into place, the deepest questions remain stubbornly open, and the honest scientist holds them open, rather than forcing a premature resolution. We do not know with certainty how the first galaxies grew so fast. We do not know exactly how the first black holes reached such mass so early. We do not know whether the disagreement in the expansion measurements will be resolved by better data or by new physics. We do not know whether the timeline of the early universe will require a modest correction or a deeper revision. The picture is assembling, but it is not yet whole, and the spaces between the pieces are where the future of cosmology will be written. To stand here, at the edge of the assembled picture, looking into the spaces that remain, is to stand exactly where every great discovery has always begun. And so we come, at last, to the questions that no telescope can answer, the questions that remain when the science has been laid out and the data carefully weighed. What does it mean to be a creature who can know these things? What does it mean to live a brief, warm, conscious life inside a universe this vast, this old, this strange, this indifferent to our presence? These are not questions of physics. They are questions of meaning, and they have followed humanity for as long as we have looked up at the night and wondered. The early galaxy at the edge of time does not answer them, but it sharpens them, the way the cold sharpens the breath, and it asks us to sit with them honestly. Perhaps the vastness of the cosmos and the smallness of our place within it is cause for a kind of quiet despair. Perhaps when you truly grasp that the universe is 13 billion years old and we have been here for the merest flicker, when you feel the weight of the distances and the cold and the silence, the only honest response is to conclude that nothing we do can matter very much against a backdrop so immense. Perhaps our discoveries, our cities, our loves and our griefs are dust on the surface of an ocean that neither notices nor cares. Or perhaps the opposite is true. Perhaps the very vastness that seems to diminish us is what makes our awareness precious beyond measure. Because in all that cold immensity, on at least one small world, the universe woke up and began to understand itself. And that awakening is rarer and stranger and more valuable than any quantity of empty space. Perhaps meaning is something the universe contains, waiting to be found, written into the structure of things. Or perhaps meaning is something we bring, something we make, a warmth we generate against the cold rather than discover within it. These are old questions, and thoughtful people have answered them in opposite ways for thousands of years, and the early galaxies do not settle the debate. They only widen the stage on which it plays out. A universe that built its first galaxies faster than we knew is no more and no less meaningful than the universe we imagined before. What changes is not the meaning. What changes is the scale of our wonder. These questions have no universal answers. Different people, contemplating the same cold, vast cosmos, will arrive at different truths, and each of those truths can be held with integrity. Some will look at the early galaxies and feel the chill of cosmic indifference, the smallness of the human story against deep time. Others will look at the very same light and feel a fierce and grateful astonishment that they should be alive at all, that they should be capable of catching this ancient light and pondering its meaning, that the universe should have produced, in its long unfolding, a creature who could look back at its own dawn. Neither response is